Okay, so this is the so-called rigorous definition of a limit, but we're going to stick with the other one. However, if you want to read it, you can read her explanation here and here, which brings us down to the rigorous definition. She also does an example using, using the definition here, the rigorous definition, but again, we're not going to do that. Okay, so here next we talk about some terminology that we're going to need. So we talked, remember, about this equation before, and this was would be a sphere centered at A and with a radius of R. So maybe a picture like this, but we're talking about Rn, so maybe we couldn't picture it, but when we were talking about R3, it would look like this. Now, if we change this equal sign to less than or equal to, then we're talking about not just the surface, but the entire inside of the ball. And when we use less than or equal to, we call that a closed ball. Whereas if we use just less than, we call that an open ball. And if we're talking about the open ball, then it actually doesn't contain the surface. So it's a solid ball without the boundary sphere. So this one has the equal sign in it, so it contains all the solutions to this. That means it contains the surface, but it also contains the inside. But this one only contains the inside, but not the surface. And that's referred to as an open ball. So she says we don't have to keep this in R3. This could be in Rn. Of course, we can't picture it, but we can still define. We can still call it an open ball, even though it might be in R10 or whatever. And we can still call this the closed ball, even though it could be in any R, R2, R3, or whatever. So she says, while we cannot draw sketches when n is greater than 3, we can see what 1 and 2 mean when n is 1 or 2. So we were talking about R3, then we get this ball, but what does it mean in R2? So maybe you'll see that in R2, it means a circle. Well, this would mean a circle in R2, and this would be the circle and the inside of the circle, and this would only be the inside of the circle. So that would be for R2, and for R1, we mean actually just an interval. So we might mean like this open interval. That would be if we were talking about R1 and we were talking about this, just the strictly less than symbol, and we would be talking maybe about something like this. We might use this symbol for the closed interval. That would be in this case. No, sorry, that would be in this case. So we see what they mean for R1 and R2 and also R3. So here she says this is the open ball, which is, we could call it a disk in R2. So that's this one. And, sorry, the open and closed one. So this is the closed ball or closed disk. We could call it a disk if it's R2. And this is the open disk in R2, centered at A with radius R, centered at A with radius R. And here, the open and closed, the closed and open balls are actually intervals when we're talking about R. And we're talking about this. We don't need the norm anymore. We just talk about the absolute value of x minus a is less than or equal to. That would be the closed one. And this is the absolute value of x minus a is strictly less than r. That would be the open one. So you can see the dots here, whereas the open circles here to indicate that these points are not included here, whereas they are included here. Okay, the next concept in the so-called topology of Rn. So we have the opened and closed balls as part of what we mean by the topology. The set X in Rn is said to be open. So now we're not just talking about open balls, but what we mean by an open set. If for each point in X, there is some open ball centered at X that lies entirely within X. So let's see a picture of that instead of... Okay, so let's take an example of R2. And suppose our set that we want to know whether we're going to call this set X open or closed. So here we have this set X. It's a subset of R2. It happens to be a rectangular set. And the dashed lines mean that the border is not included. So are we going to call this open or closed? Or a set doesn't have to be one or the other. It could be neither. But anyway, can we call this set open or closed? So the idea is that if you take any element of the set, so here's an element of the set, and can we draw what we mean by an open ball? So we can use that concept here. So can we draw an open ball around this point? So we can see that in this case we can. Now, not every open ball around this point. Can we draw an open ball around this point that is contained in X? So, yeah, here we have an open ball around this point which is contained in X, but not every open ball around this point will be contained in X. So, for example, excuse my drawing, but this is supposed to be a circle, and this could be, if I'm not including the border here, then this could be an open ball around this point, but it's not contained in X. Okay, let's go back and review this again. So what do we mean by the fact that X is open, or what do we mean by the fact that X is closed? So the idea is if it's going to be open, then we should be able to take every point or any point in X and be able to draw an open ball around it that is contained within X, entirely contained within X. So here is an example. We're not saying that every open ball around the point has to be contained in X, but just that we can find a small enough open ball that is contained in X, and that has to be true for every point in here. So no matter how close, so here's another point. So can I find an open ball around this point that is entirely contained within X? Yes, I just have to draw it really tiny and it will be true. Okay, so so in that case we're going to call it open. Now what do we mean by, what's a case when we can't do that? Okay, take this set. Now by this set we mean to say that we're including the border. So this set we weren't including the border, so we didn't have to worry about drawing an open set around a point which was on the border. So I didn't have to think about this point. Okay, but here the border is included in X. So is that going to be an open set or not? So take a point on the border, and can you draw a ball around it that's entirely contained in X? Well, no, you can't. Here's if you take this point, then no matter what circle I draw around it, some of the points are not going to be in X. So we won't call this set open, because you have to be, of course, if I choose this point, yes, I can do it, but it has to be true for every point. So it's not true for every point. It's not true for this point. There's no open circle around this point that is entirely contained within X. So this set X is not open, but this set X is open. So that's what they're saying here. Let's take a look at the definition now. Okay, so we're going to define what we mean by a set being open in Rn. We're going to define what we mean by a set being closed in Rn. Okay, so let's read it. So a set X in Rn is said to be open in Rn if for each point X in our set, there is some open ball centered at X that lies entirely within X. Okay, so we saw that. A point X, okay, the next thing we're going to define is what we mean by on the boundary of a set, or the boundary of a set. So what do we mean by saying that a point is on the boundary? So this point is on the boundary. So, but we want to define what that means. So a point X in Rn is said to be in the boundary of X. Sorry, a point X in Rn is said to be in the boundary of a set X in Rn if every open ball centered at X, no matter how small, contains some points that are in X and also some points that are not in X. So why do we call this point a boundary point? Because if you take any open ball around this, you're going to have some points that are in there, in X, and some points that are not. So suppose I had a point over here. So suppose I had this point. Is this on the boundary of this? Well, we wouldn't think so, but let's check the definition. So what is the definition? So does every open ball that I draw around this contain both points in X and points not in X? Well, clearly no, but let's say I could draw this open ball, and now some points, it's not a very good drawing, but now some points are in this open ball are in X and some points are not in X. So you might say, okay, well, that must be a boundary point. But it says if every open ball. So how about if I check this open ball around this point? Does this have points that are both in X and also points that are not in X? No. All of the points in this open ball around here are not in X. So not every open ball around this point contains both points in X and not in X. So therefore, this is not a boundary point. But here, again, no matter how big or small I draw a ball around here, I'm always going to have some points which are in here and some points which are not in X. Now, how about here? Okay, so suppose, is this a boundary point? So, of course, if I draw a big circle, then some points are going to be, in this ball are going to be both in here, and some are going to be not in here. But not every ball. So if I draw this ball around here, then no, all the points in here are in X. So this point is not a boundary point, or not on the boundary. Okay, so now we have a definition for what we mean by a boundary point. Okay, next we want to define what we mean by whether a set is closed in Rn. So a subset of Rn, we want to say, is it closed or not? So a set is called closed if it contains all of its boundary points. So now we know what the boundary points are. So, oh, by the way, how about here? We didn't check in this case. What about here? Is this a boundary point of this X? So if you draw a circle around it, some of the points are in X and some of the points are not in X. And no matter what circle we draw around it, that's always going to be the case. So this point is a boundary point of this set X. However, notice that this boundary point is not contained in X. So what do we mean by a closed set? This set was an open set. What do we mean by a closed set? If the set contains all of its boundary points. So this set the boundary points are along the edge here, and the set contains all of those. So we will call this set a closed set. Okay, so let's read it. So a set X in Rn is said to be closed in Rn if it contains all of its boundary points. Okay, and the last term we want to define is the neighborhood of a point. So the neighborhood of a point, X in X, is an open set containing X and contained in capital X. So this is the neighborhood of this point. This is also a neighborhood of this point. And for this point, a neighborhood could be, for example, that, or a bigger circle, but this would not be called a neighborhood because the entire neighborhood must be contained in X, so that wouldn't be called a neighborhood. Okay, next thing she says is it's an easy consequence of this definition that a set X is closed in Rn precisely if its complement, Rn minus X, is open. So this set here is closed if its complement, which means we take all of this is R2 actually, so we take all of R2 and we take out X, we take out all of the points in X, and you should see that the result will be open. So you can think about that, you can check it. But so therefore, if when we take out X from Rn, where X lives, and the result is open, then X is closed. So you can check that or think about that. Okay, so here, what are they talking about here? The set of all points X comma Y in R2 such that X is less than 1 and greater than negative 1, and Y is less than 2 and less than 2 and greater than negative 1. So this is going to turn out to be open. And you can see that basically because these don't have, this is not less than or equal to, this is not less than or equal to, this is not less than or equal to, and this is not less than or equal to.